This video is on solid revolution, and here I have this yellow region right here, and I'm going to revolve it about the x-axis, and I want to find the volume of the solid using the shell method. This is the yellow region that I'm going to revolve about the x-axis here. So the graph is the x equal to negative y minus 2 squared plus 9. And so the yellow region is bounded by this graph and the y-axis and the x-axis here. And then we're going to revolve it about the x-axis. And when we revolve it, this is what it's going to look like. So here's the yellow region, and then when we revolve it, we get a solid like this. And notice that the solid does not have this. This look like a cone right here. So the top is going to be there's no cone up here, and so we want the volume of this solid. And for this example, we can use the shell method. Shell or cylindrical shell, and so I'm going to divide this solid here into many shells. And so here I'm going to divide it first. I'm going to divide it into 10 shells like this, and then eventually to get the exact volume for the solid, then we need to divide that into an infinite number of shells. So let's take a look at shell number 1 here. Now shell number 1 is going to be between y equal to 0 and y equal to 0.5. The distance from the axis of revolution to here is 5, and I'm dividing this solid here into 10 shells, and therefore the thickness of each shell is going to be 0.5, and we'll denote it as delta y. So the first shell is between y equal to 0 and y equal to 0.5, and therefore the midpoint, or right in the middle, is going to be 0.25. Because the axis of revolution is the x-axis, the average radius is also going to be the midpoint, which is 0.25. So the average radius is just the point right in the middle of the two shells. To get the volume for this shell, we need the average radius, we need the height, and we also need the thickness. And so the thickness of the shell is just 0.5. And then to get the height is going to be the distance from the bottom here to the graph. And so we want the distance from the y-axis to this point right here on the graph. So we can use the midpoint which is 0.25. So we're going to do g of 0.25, and that will give us the distance from the y-axis to the point on the graph, this graph right here. And so we plugged in the place of y, we plugged in 0.25, and then simplify, we'll get 5.9375. And then the volume for this first, for shell number 1, is going to be 2 pi times the average radius of 0.25 times the height of 5.9375 times the thickness of 0.5. Then we'll get 4.6633 for the volume of shell number 1. And then in terms of y, this is how we write it. 2 pi times y sub 1 star, which is the midpoint, and then g of y sub 1 star, that's the height of the shell, and then delta y is the thickness. And then here is shell number 2. Shell number 2 is going to be from y equal to 0.5 to y equal to 1. And so the midpoint will be 0.75. the average radius, which is the distance from the axis of revolution to the middle of the shell, and in this case is also 0.75. To get the height for this shell number 2, we need the distance from the y-axis to the graph. And again, we're going to use the midpoint. So right here at y equal to 0.75. And in the place of y, put 0.75. So g of 0.75 is 7.4375. And so the distance or the height of this shell, which is the distance from the y-axis up to the graph, is going to be 7.4375. So that's height of shell number 2, and then thickness of shell number 2 is still 0.5. So the volume of shell number 2 is 17.5241. And then here are the other shells. So altogether, the volumes of the 10 shells is 460.43. And in summation notation, this is how we write it. I runs from 1 to 10. And then we have 2 pi, and then y sub I star. This is the average radius. G of y sub I star. This is the height of the ith shell. And then delta y for the thickness of the ith shell. And altogether, 10 shells is 460.43. And so the volume of the solid that we want without this cone right here is approximately 460.43. And then if we want a better approximation, then we need to increase the number of cylindrical shells, meaning we need to divide this solid right here into more shells. So let's say if we divide it, instead of 10 shells, if we divide it into 100 shells, then the thickness of each shell is going to be 0.05. And then we'll go through and add the volumes of the 100 shells. Then we get 458.17. And then here's the summation notation for 100 shells. Again, y sub I star, that's the average radius. That's the distance from the axis of revolution to the middle of the shell. This is the height of the shell. This is the thickness of the shell. And then here's, if we divide the solid here into 10,000 shells, then the thickness of each one is 0.0005. And then add the volumes of 10,000 shells together, we get 458.1489. And then here's 100,000 shells. So I'm dividing this solid of revolution here into 100,000 shells. Then we get 458.1489. And now if I divide it into a million shells, then we'll get the thickness of each shell is going to be 0.00001. Then the volumes of the 1 million shells is 458.1489. And then here's the summation notation right here, I running from 1 to a million. And so, but this number right here is still just an approximation for the volume of this solid of revolution. So if we want the exact volume, then we need to let I run from 1 to infinity. So now let's go find the volume of, let's go find the this infinite sum. And so here's the infinite sum right here. So instead of writing I running from 1 to infinity, we write this as I running from 1 to n with the limit of n approaching infinity. For this particular example, g of y is negative y minus 2 squared plus 9. So g of y star, then in the place of y we just put y sub y star. And then when this limit here exists, we defined it as the integral from 0 to 5, and then here's the 2 pi, and then we have y, and then y minus 2 squared plus 9, and then dy. And then the 0 and the 5 here, if we look back at the graph, this volume here, it runs from y equal to 0 to y equal to 5. So y equal to 0 to y equal to 5. So that's where the 0 and the 5 here come from. And then simplify 5 here, we get minus y to the third plus 4y squared plus 5y. And then the antiderivative would be negative y to the fourth over 4 plus 4y to the third over 3 plus 5y squared over 2. Evaluating from y equal to 0 to y equal to 5, then we'll end up with 875 pi over 6, which is approximately 458.15. And then if we compare this value right here with the case where we divide the solid revolution into a million cells, we see that the two numbers are very, very close. And so in summary, the exact volume of this solid revolution here without the cone is 875 pi over 6. And that's the end of the video.